Hello, fellow mathematicians, and welcome back to a video about the Gaussian integral. Now, this is really important for statistics because if we look at, people's IQ and stuff like that, it will follow this pattern, which is exactly this expression. So if we want to use this in statistics, we will actually have to find out the total area from negative infinity to infinity of this graph, which is expressed here. And now, if you might have tried solve it on your own, but it's actually very hard because it has a non-elementary solution, which means that you can't do a u-sub or some regular strategy. So in this video, I'm gonna show you how to solve this integral using changing the variable from Cartesian to polar coordinates. So to try to solve this integral, we will actually start by squaring it, giving us the same integral as before, but we can also add another one now with the y variable, which is going to be useful for later. So, in order to have this, we can actually combine these integrals and form one double integral that looks like this. And it goes from negative infinity and negative infinity to infinity and infinity. And now, from this, this is just the real, so we can actually rewrite this into the real squared, and we can just take this expression and factor out the negative. Yes, so now we want to change this integral into this integral by switching from Cartesian to polar coordinates. And now we want to represent this as a rectangle with side lengths dx and then dy. And now this is going to give us the area which we are looking for here. And if you want to look at the area of this, we can think a circle sector that looks a little bit like this, where we have this delta theta and this delta r, and the total r. And now we want to find this area, and this will now, so we can change from x and y to r and theta. And then we will also switch the function and the interval. So to solve the area of this part, we want to find the total area of this circle sector and then subtract this inner part, and the total is r plus dr, and that squared times pi to get the area of the circle. And now, because it's a sector of the circle, we'll have to multiply by the angle, so which will be delta theta all over 2 pi, and then subtract the inner, which is just r squared pi times delta theta over 2 pi. And now, because these match, we can factorize out them and then expand this, which will give us the delta theta over 2 pi and then r squared plus 2 delta r plus delta r squared minus 2 minus r squared. And now we can cancel this and this and these, and that this will shrink much faster than this other term, and will therefore lose all importance for and will therefore not be important for these calculations, which will give us the delta theta over 2 times 2 delta r. And now we can cancel these two, times r, I'm sorry, I forgot that one, which will just, and now when we shrink this delta to 0, we will get r dr, d theta. And now this will be equal to the dx and dy, and we will see that here we have the Jacobian coefficient. And now we're ready to plug this back into the original integral. Now we want to plug these results in, and so we will still be left with a double integral. And now x squared plus y squared is equal to r squared by definition. So this will just be e to the minus r squared. And now we found the change in variable will give us r for the Jacobian and then dr d theta. And then we want to think about the interval we will integrate. We can think of, instead of square, where we integrate like this and then do each one, we can think about having a line and then rotate it over the origin. So we will have from 0 to infinity of this line we integrate, and then we want to rotate all, so we will go from 0 to 2 pi. And now we are ready to solve this integral. Now that we're left with this integral, I actually want to change the order, which we are allowed to because this is continuous. So it will be from 0 to infinity of 0 to 2 pi e to minus r squared r. And now this is a constant with respect to theta. So we can actually get that this will just be 2 pi times this, which means that we get 2 pi from this, from 0 to infinity of e to the minus r squared times r dr. And now this is pretty easy. You just do a u sub with negative r squared being equal to u. And what we're gonna find is we're gonna see that minus 2 r dr is equal to the du. And now we actually have these two, so it will just be minus pi from integral. And now we want to change the borders, so plug in r for 0, we get minus 0, which is 0. And now here we plug in infinity, we will get infinity squared, which is still infinity, but it will be a minus, will be from minus infinity, and we will get e to the u du. And lastly, this is pretty easy to solve. It will just be e to the u. And now we just have to do it from 0 to negative infinity. And what we will see is we can factor out pi. We will get pi times a negative e to the negative infinity, which will be 0, minus negative e to the 0. And now this will of course be 1. So we'll actually get pi times 0 plus 1, which is just pi. So now we know that this whole integral squared is pi. Remember, we squared it in the beginning. So now we actually want to change back. So therefore, the answer will just be square root of pi, which I think is pretty amazing. So that's how you solve the Gaussian integral by changing from Cartesian to polar coordinates. And thank you guys for watching, and see you again next time.